Hey folks, I got hopefully a quick example with a spring, and I want to talk about sign a little bit on this one and exercising care on sign. Okay, so if you need to take a moment to write the stuff down that I've got here, and I'll kind of explain what I've got. I've got a compressed spring, and it's compressed 8 centimeters from equilibrium. So here's point A. Um, when the edge of the block gets to the equilibrium part here, then the spring is no longer compressed. So the spring is compressed 8 centimeters. We're going to have the block start from rest. There's no friction. The spring constant is 10 kilonewtons per meter. And we're going to determine that the power being delivered by the spring to the block at point B, so when the spring is still compressed, 3 centimeters. Okay, so again, if you need a moment, go ahead and pause. All right, so how do we do this here? So you might recall that the energy stored in the spring is 1/2 kx squared. I want to use the integral with this, and I want to talk very carefully about sign when we do this. Okay, so in order to figure out the power being delivered by the spring at point B, I didn't know how fast that block is moving at point B. Okay, and in order to do that, I've got to figure out how much work the spring did while it pushed the block from A to B. Okay, so we know that work, the most general definition, is the integral of F as a function of r dot dr, and there's going to be limits, r naught to r final. All right. Well, in this case, our r's are x's. So we're going to integrate from x naught to x final. The force of a spring. Now, here's the first and probably the most important sign thing you're going to do here. The force of a spring is negative kx. Okay. Now, let's talk about what that means for a second. If we compress this spring to the left, as we have here, the spring is pushing to the right. Okay, so that's where that negative comes from. The spring is pushing the opposite way that you've moved it, basically. All right, and then dx is here. Okay, so the limits of integration. Now here, I'm going to be very picky with sign, but this part is actually, I'll show you, it's not going to actually matter. But if we call equilibrium 0 for the spring, I'm actually displaced to the left of that. So x naught would be negative 0.08 meters. I'm converting the centimeters to meters here. So 8 centimeters is 0.08 meters. And then the negative 0.03 meters. Okay. And then we're integrating negative kx times dx. Okay. Well, the integral of negative kx is negative kx squared over 2. Okay. Or better, you would have done those better as negative 1/2 kx squared. Okay, now having said that, there's a negative here. Okay, and again, that's because as the spring is displaced left, it's pushing right, so we had a negative in there, and we're evaluating this from negative 0.08 to negative 0.03. Now, before I do all that, would you get a different answer if you evaluated it from positive 0.08 to positive 0.03? No, because you're squaring those and the negatives will go away anyway. Would you get a different answer if this were positive? Yes, you would get the opposite of the answer, and I'll talk about that in a moment. So the negative here is actually, that negative is actually important. Okay, so we got negative 1/2, the K was given as 10 kilonewtons, which is 10,000 newtons per meter, times the final is negative 0.03 squared, and then minus negative 1/2 times our 10,000 times our negative 0.08 squared. And for that first term, I got a negative 4.5 and then minus negative. And for the second term, I get 32. Okay, so this becomes negative 4.5 plus 32, which equals 27.5 joules. Okay, so that's the work done by the spring. Now, in general, we know the work done by the spring is going to be positive because as the block moves to the right, the spring is pushing to the right. So that should be positive work. So if somehow you got these reversed, if you did 1/2 times 0.03 or positive 1/2 times k times 0.03 squared minus 1/2 times 10,000 times 0.08 squared, you got a negative 27.5 here. You know it should be positive. Just flip your signs, okay? All right, so then you got that, and then to figure out the velocity of the block, so all that work became kinetic energy of the block. So the kinetic energy of the block, which is 1/2 mass velocity squared, solving for velocity, you get root 2k over m. Now, this is a different k. I'll put a little e next to it. This is a kinetic energy, not the spring constant, okay? And so we got 2 times 27.5 over the mass of the block, which we gave you to be oh, I didn't give you that. All right, let me tell you what that is. It is 10 kilograms. All right, so that's like a small book bag. Okay, so we'll put a 10 down there. And if you do that, I get root 5.5, which the calculator gives me 2.35 meters per second. So it's not moving very fast. It's only about 5 miles an hour. And then to find the power, okay, so I'm asking you, oh, that's not a vector. I'm asking you for the power delivered at the moment the book is at point B. So that is instantaneous, I-N-S-T. So that we're going to use our force dot velocity there, okay? Now, the force is negative kx, okay, and then times velocity. Now here, that negative x does matter. Okay, so we've got negative 10,000, okay, times x, which is negative 3 centimeters or 0.03. So here the negative does matter as far as the sign of our answer goes. And then we multiply that by the velocity that we just got, which was root 5.5, or you can plug in your 2.35 there if you want. And if all the negatives drop out, and I end up with 704 watts. So that means at that moment, that spring is supplying 704 joules per second to the book bag, and it's still accelerating it forward, okay? Now, same thing here with the sign thing. You know the spring is pushing the book to the right, so you know the power's got to be positive. If the force is to the right and the velocity is to the right, then this dot product here has to be positive. So you know, well, no matter what you get here, you should put a positive answer in for your answer because you know the spring is adding energy to the book bag. So I hope that example was helpful. Be very careful with sign, and I'll see you on the next one.